maybe you can share a bit what you do. So what is your expertise? Technical background, maybe you want to start? You on the front row?
So I'm from a cloud engineering perspective.
Okay. More interested in a backend than in the application itself, or?
Yeah, definitely, I would say.
Okay. 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 You?
So my background is geoinformatics.
Okay.
Actually, why I'm interested in this is because we're working on some digital twin prototype, and we're thinking of there's some discussion on using CWL as a workflow orchestrator or workflow composition.
Okay.
Yeah, and that's why I'm here.
This is good to pick up. Thank you.
Cool.
Okay, hi, I'm John Trockenbrot. My background is mostly in radar remote sensing, synthetic aperture radar. And in recent years, I've developed a new analysis-ready data product, Sentinel-1 normalized radar backscatter for ESA. And so I'm working at DLR for the Terabyte platform, so a large compute platform that we're setting up. And so my current role is basically to take this NRB specification that we set up and scale that up to a systematic product in a petabyte scale to provide that to our users on the platform. And so looking also into workflow management systems
Okay.
here.
Yeah. Your name sounds really familiar to us.
So, hello, my name is Agris Browns, and basically I'm from the Institute for Environmental Solutions based in Latvia. And my background is physics, but I work as a remote sensing researcher.
Okay.
And it's basically every day-to-day work is based with satellite data workflow or pipeline creation. And,
Okay.
Yeah.
Hi, I'm Francesco from Cineca, and I'm working mainly on cloud technologies. I'm a cloud engineer in the HPC department, so we are involved in many European projects, and I'm very interested in this topic. I already saw CWL, so I'm interested in seeing something more.
Okay.
Hi, I'm Lucio. I work for Reference. I write data processing pipeline for satellite, so this is why I'm interested.
Thank you.
Okay.
Thank you very much.
So thank you for that introduction. I'm really happy that you have a solid technological background, let's say, because there is some light programming skills here, light knowledge about YAML and Python. The examples here are Python. So we have tried to reduce the complexity of the exercises to the bare minimum. So you will definitely recognize that the application could have been packaged as a single step. But on the other hand, we went for the full fan-out model of the application, okay? So we have published a guide online, and this is the URL that you will find. So you may open it on your browser. It will definitely help you copying and typing the scripts that you run on the environment. We have set up a code server pod for you, and it provides the environment to run this. Although we are running on this environment, which is a pod on the cloud, most of the exercises would run on your computer if you have Visual Studio as your IDE, Podman or Docker, and the CWL tool, CWL runner. So there's nothing too complex about this environment that you cannot reproduce on your own computer, except for the part when we will run the workflow on using Kubernetes resources, where you definitely need a Kubernetes cluster. And so this pod here is able to spawn additional pods, and this is why we have the capacity of running CWL on Kubernetes in this environment. So, okay, in terms of a light introduction to oh, that's not the one. Sorry for that. Oh God. Well, I think I will skip that presentation because I have the same content here anyway. Okay. So during this event, we will learn about the fundamentals of the EU application packages and their role in the Earth observation domain. We will learn how to leverage the common workflow language to describe package and share workflows, techniques for incorporating data, code, configuration files, and documentation into an EU application package. So the goal here is to build containers and have them orchestrated by the common workflow language, run them in 2 different execution scenarios. And this is what we have written in a set of best practices for creating portable and reproducible Earth observation workflows. And the hands-on exercises are here to reinforce what you learn in the concept. So there is an incremental pace. The process is quite simple. In the end, we start from command line tools. Whatever piece of code that you write could be Python, MATLAB, and so on and so forth. C, you actually expose a command line interface, package that command line interface in a container, and then wrap that command line tool in, around the CWL objects that we will see later on. And then you test one of the applications on different execution scenarios. So these are the steps that we will follow. We will use a water bodies detection application. It's a very simple application based on the NDWI. So we will do the normalized difference between the green and the near bands. And we will take the fact that ranges from 0 to 1 are water surface, and ranges flooding humidity from 0 to 2. And so on and so forth. But we will have a step that will determine that threshold here using the OTSU automatic threshold. So it's an additional step in the process. There is an interesting scenario here because I'm going to present you 2 different scenarios. This is the workflow that represents what the application will do. So it will take a stack item. So it is using the spatial temporal asset catalog item to recognize what it has to process. It will crop the green and the near bands, and those tasks may happen in parallel because there is absolutely no relationship with or dependencies with them. Those 2 will generate crop the green band and the crop the near. You should be reading near here. Apply then a different step, normalize difference, which will generate another geotiff. Apply the threshold, and we will have the OTSU.tiff. And then in the end, we have a step that generates another stack catalog because both stack is used as the manifest for inputs and is used as manifest for outputs. So in the end, we will have a catalog JSON, an item.json, an asset with the OTSU. Are you familiar with the stack specification, or should okay? We will look into details, but it is. Then we have another scenario where it is much less cloud native process, where we first stage in an element from a stack item. All the assets become part of a local storage. And then the application package reads, instead of reading a remote asset on the cloud, it will read all the files from the local file system. Those are 2 different models that you have, cloud native processing or processing with local data. But the model then doesn't change, so we will scatter on the green and near bands and generate the same thing and the same storage. This is the representation as a CWL workflow with the 2 steps here. This is the data that we are going to use. So we were mentioning a stack, so we can open this in the new tab. Stack, in terms of, for those not too familiar with that, is a GeoJSON on steroids that allow you to describe what the product contains. So if you're familiar with the Sentinel-2 product, you know that it has a manifest according to the safe specification. It has a bunch of XML files, and for processing Sentinel-2, you will have to learn about that format itself. And then if you start working with Sentinel-1, there's another manifest, another file structure behind that, another set of XML files. If you go to Sentinel-3, you have yet another manifest with a different file name, and the files will be netcdf. Asset stack will actually abstract you from that complexity and provide you with a set of properties regarding a product, defined with extensions on the stack specification itself. But the most interesting part about this is that if you want, let's say, let me get there. If you want the blue band, for instance, you have a stack element, an asset, that will have a title. It will have the reference to the TIFF file or the JPEG 2000 file, whatever, but it will bring additional information. So in the end, you don't have to know that the blue band is actually B02. You just have to look for an asset that has the EOBand's common name property blue, and that will work for Landsat, for Sentinel-2, for Pleiad, or whatever other mission that you're working. So Stack kind of brings an abstraction on the file system or on the location of the assets. This is not a file system, this is a HTTP reference, and this is why we have this as an input to our application package, because we no longer rely on the code that will look into a folder for geotiffs that have the pattern B02 star.tiff, and if it's another mission, it will look for B07, and we're always talking about red, green, near, or whatever bands, okay? In terms of the application steps, we have, as you have seen, we have the crop step. Here is the description. So this is where we stand in our workflow. The purpose is to crop an area of interest expressed as a bounding box, either with Sentinel-2 Landsat 9 data, and generate the crop green and the crop near base. So the code is a simple Python code, not too long. It exposes a command line tool interface with the click, and it does a simple crop operation using raster IO. So it will read the stack item, and it will find the band that it is looking for according to this parameter here, and it will crop the product with the raster IO library, okay? So running the step, so I will run. So have you started you'd rather look at the presentation and stick to that, or work on your own environment? Just tell me so that I can adjust to the information. Your own environment, okay. So you have opened the environment, right? You have something duplicate. You have something like, just keep it like this. And you have a README. Okay, so this, you have a README on the /workspace, right? I will invite you to git clone this environment here. For that, you can click here, open a terminal, and just copy this, paste this. It will not work because I already have it, but on your environment, it will definitely work. Okay. Then I would invite you to open a new tab on your browser, and with this, you can do right-click, duplicate this, and instead of workspace alone, you just type, you will type something else later, okay? So let me go with where you are. You can do cd app package training bids. Okay. And this we no longer need. And this. So the first step of doing the first script to run is to run this here. It will set up a new folder on your environment. And you just type this here, paste, and you have a /runs folder, okay?
Sorry, if you have also any more specific question, you can also ask, and I can come and talk
Okay.
to Fabrice. Okay? As we go through the process of the scripts. Just show.
Okay, so in terms of a simple best practice that we enforce here as an example, it will help us understand what the container does. We will create a Python environment using the standard VM library. So it will actually create the environment, activate it, and install all the libraries that we need for run the crop step. So I will just type this here. No, I'm not in the right environment, sorry for that. Okay. And that will provide you the environment that we need. Okay, so it might be useful to well, no, we can leave it here. Okay. Do you have your Python environment done? Okay. Now we will run this Python code using the parameters. We provide the -mice input item and the resource to the stack catalog, the area of interest, the code, and the band that we want. So we will run, again, we will run this. It will take a few seconds. So you see that it is actually reading. Let me get the pointer. It is actually reading the GOT from the Amazon, writing the cropped file, and it's done. So we haven't downloaded any piece of data. Okay. So we'll do the same for the near band. Let me copy this. One too many. And again, the difference before is that using the common band names, we didn't have to know that the near band is BiDS'23 in Sentinel-2. It's actually information that we don't care. We want the near band, and we just leave a stack to deal with it. Okay. So I'm doing it twice. So far so good. We have a small Python script that knows how to crop bands expressed with the common band names. So if we see the content of the folder, we have the Python environment, that's a bit more, but if we ls all.tif, we have the green crop near tif, and this is what we expect out of this step. This is what we have to do. So now we can deactivate the Python environment. And you see that we're back to the basic environment. So we will do that for the remaining step. Now I will apply the normalized band. The setup is already done. I will create environment for running the normalized difference. There we go. The normalized difference is an application that applies the normalized difference, and in this case we simply use raster IO to write the array 1 minus array 2 plus 1 plus 2, and the command line interface is simply this: you provide the two rasters, and this is exactly what we're going to do running the step. So if you have created your environment, you can run now with this small script. You can run the normalized difference. It will take as input the crop green and crop near, and we have the normalized difference band. We hurry up to deactivate this environment, because this is not the most important part of the training. And we now go for the Otsu threshold step, and this is where it takes the normal difference TIFF as input and applies the Otsu threshold to the TIFF. Again, to run the step, you will create the Python environment. That installs all the dependencies that we need to run this step. Okay. And now we can run the command line tool for the Otsu threshold here, taking as input the normalized different TIFF. Let me open this, paste the command, and you see that we have run this. It runs really fast. Now, okay, now it's maybe a good moment to stop and find minus name all.tiff and just miss. Okay. Okay, so we have a few tips on the file, and Otsu is actually our detected water bodies. So you will agree with me that Otsu.tiff is not the best information to convey around the result. So file name is definitely not the key here. So the last step that we have to do is to create a stack catalog. So it will read the stack item as the input information on our data. It will read the Otsu.tiff to generate all the information around that. We need the input stack item to get information such as the start time and time of the acquisition, because nothing has changed in that context. The geographical boundaries of our product is of course different from our input because we did a crop here, and so the Otsu has a different shape, but the code will definitely run that with a small utility from RioStack library. It will create the stack item, and you provide a geotiff. We provide the metadata, and we have all the information to generate our stack item. So, oh, I forgot to deactivate my Python environment. Let's do that. Deactivate it. And now I will do the same as we have done before to create the environment for generating the stack, installing all libraries required to do so. And now we can run the step and see what it produces. Paste. It is actually done. Let's deactivate the environment and clean up and see, then inspect what we have on our file system. So you see, we have now a file catalog.json that we can easily inspect here. And you see that it is a simple GeoJSON file well, JSON file actually, that includes an item. And if we look at that item, we will see that we have the information about the coordinates, the projection of our file, a lot of information about the projection, a lot of information about the projection. But if we go down, we have also the date time of our result, the geometry, and we have the links. And most importantly, we have an asset called data that points to the otsu.tif. That means that the next application that would actually consume those detected water bodies would only rely on the fact that they just have to go to the data asset without knowing the file name, without knowing that the file name is on a given date, okay? So actually, this is just to introduce the application. We will start packaging the application, and now the step is to create the containers. So in our process, the developers follow the steps described below. They prepare one or more container images describing the execution dependencies of the software. And this is what we do here. So I've tried to simplify as much as I can the Docker file, and this is what you have. So we start from a Python 3.10. We simply run pip and we install the dependencies that we need. We do a small test to see that everything went well, and we add the file for each of our application, and we put that in a folder in the container. So in the end, this container does not do a lot, but what it has a set of libraries that will be able to run the crop step. And we do the same here. So you see that the dependencies have changed a bit. If we go down the stack, we have Rio stack. So we have one container for each of the applications and this. So to build the containers, we rely on Podman. Podman is like Docker. Actually, it was born before Docker. It's built and maintained by Red Hat. And we rely on Podman because it allows us to build containers in a pod on Kubernetes pod, and this is very convenient. So let me go back to this, and let's build the containers. So it was really fast on my pod because I already had the Python 3.10, but let us know if when you're done. So there is a small test to know if we have everything okay, is to list all the containers that we have on our local registry. And I don't know why, but this takes a few seconds to execute. I would expect something a bit faster, but this is how it goes. So far, so good? Okay. There we go. So you see, we have built our container. So this is my dry run 3 hours ago before I came to this session. Next step, we will test the containers. And I think that it will be enough to test a single container, right? One could advocate that, well, I've built containers. I will tell people how to orchestrate those containers, and I will provide a nice, simple recipe to run the containers. Okay? Well, it is definitely a solution that is possible, but in order to get to the point of the application, you have to write a few elements. First, you have to mount the volume so that you can get the results that are generated in the container. So this is why we mount workspaces runs, and we target on the pod, on the folder /runs. We instruct the container to run on /runs. We put read-only as true as a security measure. We set a user so that we don't have root files on your local file system. Then when you have done, We said, well, remove the container after all, provide a home environment, and update a Python path variable so that we can do Python -m app in our container. But still, well, yeah, this works. We can all that we have in this folder, and now we'll run this step, and we will see. Let me take this. This actually will run the container. Ramping up. Okay, so you see, it is actually doing exactly what we had before with the Python script and the Python environment, but this time we have a container. We will make it more obvious when we crop the near band. Okay, so if we do an ls, we have the I hope that does it. So a bit more details. You see that actually the script is wrapping the podman command and putting everything together. So yes, we have now at this stage 4 containers that know how to crop, know how to do normalized difference, apply the Otsu threshold, and generate a stack. And I'm not going to go through the exercise of doing all the steps, but you have them online if you care to do this. You see that we have highlighted the inputs, and everything should work smoothly as we have done before. Okay. Now let's move on to the CWL step. So we will prepare. This is it. Prepare the command line tool documents, wrapping the command line tools, well, in containers. So this is actually using the CWL specification command line tool to do exactly what we have done with Podman, but we will have a simple YAML file describing those steps. Okay, so how is that done? For the crop step, this is a CWL document. So it starts with the CWL version that you see here. It uses the climb command line tool. So we're telling CWL that this object here is a command line tool. We have provided it with an ID. We instruct the whatever CWL runner that it will need the inline JavaScript requirement. The definition of the Python path environment variable pointing to app. This is actually exactly what we had for Podman execution. We had to say, create an environment variable. We will define the resources that we need, the cores. Well, 1 CPU plus 512 megabytes of RAM were enough to run this. We provide a hint, which is pretty much the same as a requirement, but it is not enforced. You can run this CWL document without Docker. And we will tell them that this tool here will need this container. So we actually tell a CWL runner that this application will run in this container. The base command is pretty much the same as the one we had for Podman, Python -m app, because we had defined this variable here. We provide no arguments at this stage because we have defined them with the input. So CWL provides a very convenient way of describing every single input, its type, and an input binding. That means that when we provide the input with the ID item, it will expect a string, but it will attach the -- input item before that. So the command line that it will generate at runtime is Python -m app, -- input item, the value, -- AOI, the value, EPSG, the value, and so on and so forth. So in the end, this is what you have. Then we have defined the inputs. We now need to define the outputs. We provide an ID, and we say, well, whatever file that you find with the extension TIFF, that looks file to me, and you have to pick up something that is a file. It could be a string, it could be a folder, it could be anything. So you have a detailed information about what we have just said here in the documentation. So I will use the CWL tool runner that we have on our environment here. So if I do CWL tool and type CWL tool minus help, I will get the help. Now I can actually use this. And so we will run the first CWL object that we have here. And so this is the output of CWL'23.1. You see, it will start processing. This is the command line that is wrapped in the command line script. This is the log of our application. But at this stage, you will see that CWL actually did exactly the same podman execution that we did earlier manually. It took care of the user details. It mounted all the file systems that we needed for alone. No, we didn't have to do anything. It provided a working dir, it provided the environment variable that we asked. It invoked the Docker image that we had generated early on, and it applied all the parameters that you wanted. So in the end, we get the output, and you recognize the cropped ID here. It's a file that is on our file system. So if I do LL, I have the crop green file, and the crop near files are here. All right? So in the end, this file here, this CWL command line tool, is already something that you can share with a colleague, because they don't have to have anything else but CWL tool plus podman or Docker. And at that stage, they will be able to run this. There is no dependencies on Python, no dependency on libraries, just on CWL tool and the container engine, which is already something. Because sharing shell script, you never know if they have a Z shell or Bash or C shell or whatever. We never know what dependencies they have on that file system. This is portable. This is something that you can run elsewhere. Okay? So we will not go through all the steps, but you would find it quite a repetition of what we have saying. So we actually provide information in the guide to do every single step. Maybe the difference here that we can find is that we would have an output binding type directory, because stack, we have the catalog.json, we have the stack item JSON, we have the also TIFF. So we want actually all the content of the directory that is generated here. Okay? So we have at this stage 4 command line tools that we have defined. One for crop, one for the normalized difference, one for the Otsu threshold, and one for stack. It's now time to go to the next step, which is to prepare the CWL workflow, orchestrating CWL command line tool documents, wrapping the command line tool available containers. That's a very long sentence, but this is what it does. So I have provided several examples. So we will go through this one here in this session. We have additional scenarios for staging the Landsat. So you have description about the stage in, the stage out, and how to process a Landsat data. But we will focus at that stage on creating a workflow. For the simplest example is to take one sentinel to stack item URL and apply the processing steps that we have seen early on. Okay? So we start with the same stuff, CWL version, a bit a small number of information about metadata, software version 1.0. This is at this stage not mandatory. Big difference towards what we have done so far. We have added an element graph, which is the ID of a list. This is how CWL allows us to put a lot of definitions in the same document. And why did we do this? But because we have copy-pasted all our command line tools right here, all of them. So we have just put it as a list item in each of the things. So we have the Otsu command line tool, and we have the stack command line tool here. So what we simply do to orchestrate this with the workflow, we start writing where's my pointer? A class workflow. We provide an ID. It's a best practice to put a label, which is a title in the end, put a doc element, a longer description. We have a requirement that we need to scatter. Scatter is the fan-out pattern, is that you take a list of elements and you create an instance of a step for each of those elements. So it will have some parallel processing going on. So we define the inputs at the level of the workflow. So what do we need as inputs? We need an area of interest. We need the PSG code, as we have done before for the crop step. We need the list of bands that we need to process, green and near. And we need an item, as we have done before. So those are the inputs that you recognize for the crop step, because all the rest of the underlying steps didn't have an additional inputs. Okay? We have an output that we describe it as a stack catalog, and it will come out of a node. And we have a very important block in the workflow definition, which are the steps. First, we provide an ID. We will tell what each of the step will run. So this step code called node crop will run the element in our document with the ID crop. And where do you recognize this ID? It is here. So you know that this step will run the crop part. So it will take as input the items, the area of interest, the PSG code, and the bands. And so this is a mapping between those inputs here and the inputs for this step. And it will generate the crop, as you have seen. And we will tell them to scatter on the green and near band. This is how we will have two parallel steps in our workflow. Then the node normalized difference will run the normalized difference command line tool. It will take the rasters that were generated by the node crop. And this is how you link the second step of the workflow with what happened before. You said that the input is something that comes from another node, okay? It will generate the NDWI. Then the node Otsu will run the Otsu. It will take the output that was generated here. So this ID here is this ID here. So this is how in CWL you can map the inputs and outputs between the steps. Finally, the node stack will take the output from the binary mask, okay? Now, we will run this later on. I will just discuss a bit more about the stage in and stage out. So an application input argument that requires staged EEO products files shall be defined as an argument that points to a folder where a stack catalog named catalog.json contains a list of one or more stack items. This is what we have discussed before. Before we implemented this best practice in the Earth observation application packages, you would never know actually what you would get as an input. So we have seen so many applications that would say, this is my input directory, and then you do a find with a given pattern. Find everything that is B03 TIFF, so you would get the green band, the B08 for the near band, and we have defined a rule that this is no longer a practice that you should adopt, but you should rather rely on a stack catalog that was staged in, so that you would get different libraries to dig into that. So you abstract yourself from what is written on a file system, or rather actually the stack assets rely on your file system. You don't have to know. You will get tooling that will provide you that. Well, this translates to plugging a staging step to all workflow steps having the input of type directory. So our inputs in the workflow had the string type. If we change to a stage to process staging data, the type of the item is no longer string, it's a directory. So that will tell CWL tool that when it will run the crop step here and take this item, it will actually mount the directory on the container, and the application will find a catalog.json here. So now it's maybe a good time to look at a small detail that we have skipped in the description of the crop step, is that we have actually made our application so that it can read a folder. So if what I got as the parameter type is a directory, so I can check this, then I will use PyStack and read this folder and add the catalog.json. And that's okay, my application now complies with the best practice, because it can read an input of type directory and read the catalog.json. If not, well, we just read the item URL fine. So we have an application here. The crop step actually can work both ways, either by reading stage data or reading a remote stack. And this is why our crop step is able to process stage Landsat data or Sentinel-2 data by reference provided by that. Okay. So back to our workflow. We will focus on executing this. But first, we have to understand an important step in the process is that the application package files plus container files plus everything that we have here should rely on a software repository and be supported by a continuous integration system. And that continuous integration, what it will do, so we provide a set of best practices, but what it will do is that it will take the CWL workflow, validate it, so make sure that there are no syntax errors to do that, extract the version from that metadata field that we have seen, have the containers built for every single step with the Docker files that we have here, push the containers towards a container registry such as Docker Hub or any other container registry that you use, and push those containers here, update the CWL workflow with those remote container references, and push the CWL in artifact registry. And at this stage, you will have an application package that you can share with your peers, because the containers are available in a container registry. They will be able to do the Docker pull, and the application package has all the information to get those containers as well. And this is a big difference between what we have written here, because you will recognize that this workflow as it is here will work with our local containers that we have built. Those containers are not available elsewhere yet. And this is why the continuous integration step is important. So if we look at if I'm able to type this, I will look at the releases that the continuous integration has generated. I will download the CWL file it has produced, and you will see the difference between what we had. Okay, you will see that the crop step now is something that you can pull from in this case, the GitHub container registry. And you will see that we have used the signature of the container so that we make sure that we don't rely on the tag. And this is definitely increases the insurance that we are using the right container for what we want. Okay, is this difference between the local containers and the remote containers in the GitHub in the container registry clear for all of you? This is what ensures the portability. Any of you could go to that release and pick this document and run it with your CWL tool. Okay, and this is actually what we're going to do now. We're going to go through 2 execution scenarios, so running on a local machine. And so, well, I have this set up already. I will define that I want to use version 1.0.0 and download the application package from GitHub. And this is done with this script here. Let me run that. Okay. If I see now, I have my this application package that is downloaded. If now we will execute it with CWL tool, so it is actually the same execution as before, but this time we don't provide the command line tool. We provide everything. We provide the workflow, and we provide the same input. So let me do this. And off we go. So now we are running the application package that has been published on GitHub. We downloaded it, and we are executing it with the CWL tool, providing all the parameters. You have seen that the first step was to do the Podman pool of the containers that we have just published. So I have it locally already, but this is what CWL tool does. And it has run the green step here. You recognize the green step here with the input item. This is the log over output. And well, it went ahead. It is cropping the near step here with the container published on the GitHub container registry, applying the same command line tools that we have defined for our tools. Now it is applying the normalized difference. It will pull the container. Since we're waiting, do you have any questions? I'm happy to take them. So far, so good? Okay. So now we are at the Otsu step. Now it will produce the stack item. Okay, and this is what we get as an output. The workflow output is a stack catalog, and you see it provides a listing of a folder. If I guess I have it, we can look at this is the folder that was generated by our execution. If you look, the pattern is workspaces run and plus an identifier. So if we look at the content, we have actually the catalog.json, the stack item, plus the results that we have. Okay, and this is what it looks out running an application package that was published on GitHub, and you can, if you install CWL on your computer and you install Docker, you can do exactly the same exercise on your computer. It will run. Okay. Just if you have Docker, just remove this flag here, because that tells CWL tool to use Podman instead of Docker. Okay. Now, very nice. Working on my machine is definitely a good feature. How does this actually work on Kubernetes? Well, we have there is a CWL tool for running CWL on your machine, on a virtual machine, whatever. And you have seen that for every single step CWL tool created a pod container. Calrissian would actually rely on CWL tool for many of the operation, but it overrides the CWL tool method to create a container, and instead it creates a pod. Okay, and this is how we can have every single step being processed on a different pod on Kubernetes. And this is what will actually provide some level of scalability on your workflows. If you had like 10 Sentinel-2 to process on your local machine, well, that would take time. We will do that with Calrissian. And so this time we will download an application package that includes an additional step to process things in parallel. Let me just get that paste. Go back to the guide and see, create the workflows. We have Sentinel-2 workflow of workflows, and this is actually what we do. We take a list of stack item URLs. We scatter this larger box on every single stack item. What do we apply? Crop plus crop, scattering on each of the bands, apply the normalized difference, and run the threshold. When we are done processing every single stack item of our input list, we create the stack catalog. So this is what we are actually going to do now in the execution scenario, relying on CWL. So I have downloaded this already. I have to, let's look a bit at how Calrissian is executed. So we provide a way to create the results JSON just as the CWL tool does. This is the output of the Calrissian execution. We provide some limits in terms of maximum RAM and maximum cores that Calrissian will be able to use. So you have seen that for every single command line tool, we have said that we want 1 core and 512 megabytes of RAM to be used. This will tell Calrissian that he will be able to run pods up until it consumes the RAM or the cores. So if you have a step that requires 9 cores, Calrissian will not be able to run it. If you have an application that has 16 inputs and each of the command line tools require 1 core, it will launch 8 pods, and whenever there's a pod free, it will take the 9th product and so on and so forth. So this is a way to avoid flooding your Kubernetes cluster when you have thousands of inputs and you run out of resources for the other namespaces. And then we carry on. We provide a temporary output dir prefix. And you see we pointed to a volume on our local computer, on local environment, Calrissian/tmp. Output dir where we want the results to put. Usage report, we will look into that. The logs of the tools. We provide a node selector. So are you familiar with Kubernetes node selectors? It is a way to say where we want the pods created by Calrissian to be launched. So you could have different node pools for different processing scenarios. And if you have a node pool with nodes that have larger RAM capacities, those can be used for payloads that require a lot of processing. If you want to process our data, as you're mentioning, you definitely need 32, 64 gigabytes of RAM. That would be the way to say those processing steps have to go to that node pool, so that this is also providing a way to save money at some time. And then we provide the CWL that we want to run, and we have provided a list of a few products. So let's see how this actually works. So let's open another kubectl get pods, and you see we have a few pods running here. It has started creating a few pods. If we go here, you will see that this is the log that we have. We can put here and watch -n2 kubectl get pods. Okay. So a few of the crop steps are already done. You see container creating, terminating, container creating. This is actually Calrissian launching different steps. And we will start seeing normalized different pods popping up here after this. And yeah, you have the normalized. The first normalized difference is here. So we have the pods for the normalized difference. So this is actually CWL scaling up on the Kubernetes cluster. Yes?
Maybe I missed it. The scatter you did at the stack item level, the sort of outer stack,
yeah.
Where was that specified?
I will show you. Okay. So, okay. Let's look at that package. We have a top workflow element, okay, with a step that's called node water bodies that will invoke the workflow that we had defined earlier. So it will invoke a workflow that is called detect water body, okay, and it will scatter on the items here, and then it will run the stack node with all the outputs from there. So this is how you actually do. You add a workflow on top, and you say one of the steps in this workflow is to run a sub workflow, and you will that get spinning. It will consume everything. Oh, so we're done. So while we were discussing this, we have now. Let's see what has been produced here. So we have one stack item and one GOT for all of our inputs. We have a catalog JSON, and this is what we get. So actually, let's look at what is produced in this volume here. So we also have a usage JSON that will tell you what every single process took in terms of processing, elapsed hours, elapsed seconds, the RAM that it consumed, the CPU hours. So you have actually a report on the resources that were consumed on Kubernetes for running this application here. So this is also important information for billing purposes, because you know that this workflow actually consumed this amount of resources on your Kubernetes cluster, okay? So the results.json is what you have seen so far. It's the list that we have enumerated with all the results. And that's pretty much it. So important thing, if you want to run this /Calrissian volume on Kubernetes is actually a read-write many. And this is pretty obvious because we have this volume here, and we must have all the pods that are reading and writing. So they're reading all the inputs from here, and there are different crop steps that are reading this information from the volumes, okay? So there is also a section in the guide to have your application package become fair. So we provide a few recommendations that we were discussed in the DOGC in one of the latest test beds. The software configuration management, so that you have the README file, an authors file, a Lances file, a codemate.json file, and you will see that if you look at the repos supporting this water bodies application, I kind of rely on the code meta information for a lot of information to build the application package, the authors and everything. So that that we have that metadata here. No, not this one. Yeah, it actually says the code repository and the author of the CWL file. Okay. We also provide recommendations for the software identification and traceability, how to get this in the get your software with the associated software heritage persistent identifier by the UNESCO initiative on preserving software. And a recommendation about the application package containers identification, not relying on tags, but rather relying on the signature. It's not perfect, but it's something more. Application metadata, a number of fields that you can have: author, citation, code repository, contribution, and things like that. And so in the end, you would have your CWL with extended metadata. And then you can also link, for instance, a DOI for this. For instance, I found a paper by a Portuguese team that does exactly what this application do. If you look at their approach, it's pretty much what we have implemented, which is to read satellite images, derive the NDWI, get the OTSU threshold, and get the water maps. So I could take the DOI and, well, I could. The authors could implement a CWL and put the DOI here, okay? So this is what we had for you. So we still have a few minutes for questions and answers. Just for your information, we have a booth in the exposition area. I will be here all week. If you want to pass by and discuss your use cases, whatever ideas you may have around what you have learned so far, questions, I'll be really happy to support you in applying the Earth observation application packaging with CWL. Okay? Okay, thank you. Richard.
Well, following on from that, we also mentioned the code sprint, the OSGeo code sprint.
Yes.
Is one of the, amongst quite a few activities supporting, is for anyone really following this guide and what you've just learned to have a go and create their own application package with maybe some algorithm that you
Yep.
have, and just have a go with it really. If you're interested in joining the code sprint.
Yes, actually, we could then meet up in the code sprint and do a small group or batch of persons and see what we.
Yeah, definitely. Yeah.
If you have your own use case, or Pedro.
We'll be following up in 20 minutes in the other session.
Yes. So actually, we have another session that looks into reproducibility of this. So we have created a small story. So actually, all that we have done is made by Alice. It's a user persona. She has produced this application, and Bob is somebody that picks up on this application package and reproduces the results that were generated initially and does its own re-execution. So it's just not looking at how packaging, but taking the application package and as an object and running to the processing as well. Okay? Go.
Specific reason why you're using pods and not jobs for this kind of a workflow?
Yeah, it was actually there is a ticket in Calrissian. Jobs are too resilient, so we want things to fail first if things go wrong. But it was their first approach. So we became maintainers of Calrissian ourselves at Terra 2 with the Duke University. But their first approach was to run jobs. But too sticky. They would retry and retry and retry, and that.
Could maybe mitigate some of the nuances when you're defining the resources. But yeah, maybe this will
Yes. Yes.
That's one thing that if you want to fail.
Yeah.
Just for the television, if you could.
Sorry.
Because they are.
Okay.
Shall I repeat?
No, I think it's okay.
The question was why Kubernetes pods instead of jobs. So just to repeat.
Yeah, and yes, it was that the Kubernetes job by their nature in the Kubernetes ecosystem is they're too resilient. So with their time to live, with the retries, and the first implementations of Calrissian were based on getting jobs instead of pods. But then they moved to pod. It's a lighter approach. Okay.
If you want, you can follow us to the
Oreo session.
So is there a rule of thumb on the granularity of these jobs? So I mean, you separated it now into several jobs. First cropping the images,
Yeah.
and creating the index, and so on and so forth. So I mean, I might as well just put that all into one app, right?
Absolutely. And
So what are the recommendations for that?
yeah, this was actually what I said when discussing this application. You would definitely recognize that a single step in a single pod would definitely do the job. But I wanted to explode everything so that we have different scenarios. My experience would tell me that it is more on the amount of data that you have to move from one pod to another. If you have to move 50 gigabytes just to split two steps that have no fan-out, fan-in dependencies, then lower the data movement, because moving from a local file system and to this Calrissian volume, it's always a storage class that is read-write many. So it's either NFS or Ceph or whatever implementation your cluster have for the read-write many. That this movement of data from one pod to this environment here, and from this environment to the next pod, will definitely slow you on your analysis. So it really depends on I would say the data volume between steps is an element to make sure that you have. So for instance, in what you do, you would never split a snap graph in all the single steps in pods. You would actually try to exploit snap configuration at its best in a pod, so that you would get the best result of a single pod. Of course, if you have to do the coherence and the backscatter in different steps, well, okay, some pre-processing and then coherence backscatter. It's really the volume of data would be the rule. Okay.
So what happens if something goes wrong in between? How do I?
Things go wrong. Things go wrong.
Yeah.
When?
So how do I catch errors in between?
In here, well, if a pod, if the exit code is not 0, the workflow execution stops, and you can inspect the tool logs, the pod logs, to see what went wrong. This is, but the execution will stop. Okay, the pod has to exit 0 in order to carry on. But it really depends on the. This is not the CWL specification itself. Those are details or the implementation of the CWL runners. So Calrissian will do it one way, CWL2 will do it another, Toil will do it yet in another approach. Okay.
So this can be done with Podman, Docker, or like any containerization.
Yes. Yes.
Also, you mentioned this Toil also.
Toil is for HPC, yes. So it's actually Toil provides a layer of abstraction in transforming the containers to singularity, getting in touch with Slurm.
Yeah.
So that magic is implemented by Toil, but there are different HPC CWL runners available. Arvados, I think, is another one, and then there's one from University of Torino, which is called, can't remember the name. Yeah. Stream, yeah. Yeah, Streamflow, yeah. Jacopo, glass of whiskey. Yeah, that's the guy. Okay.
Yeah, cool stuff. Thanks a lot.
Cheers. I think I have to rush and evangelize a lot of. Thank you.